Last week, I was at a tech mixer in Palo Alto and ran into an old colleague who's now a lead architect at one of the major big tech AI labs. He was practically vibrating with a sort of caffeinated intensity, showing me photos on his phone, not of his family, but of his company's newest data center. He spoke about their cluster of 50,000 H100 GPUs with the kind of reverence usually reserved for religious icons. To him, the path to artificial general intelligence was a simple, glorious equation of brute force. More chips, more electricity, and more capital would eventually equate to a digital god. He looked at their multi-billion-dollar burn rate not as a risk, but as a moat, a badge of honor that no one else could afford. But then the conversation shifted. I brought up the latest efficiency benchmarks coming out of the East, specifically how DeepSeek had managed to match their performance using barely a fraction of the compute and power. The change in his demeanor was instantaneous. The excitement vanished, replaced by a sharp, dismissive irritation. He didn't ask about their sparse architecture or their multi-token prediction strategy. Instead, he muttered something about cutting corners and subsidized energy before dropping a line that felt strangely hollow. In the Valley, we don't optimize for crumbs, we build the whole bakery. That sudden pivot from arrogant pride and sheer scale to a defensive rejection of efficiency was telling. It felt less like a technical disagreement and more like the anxiety of someone watching a Gilded Age come to an end. It made me realize that while the West is still obsessed with the financialization of compute, treating AI like a high-stakes real estate play, a new efficiency civilization is rising. One that understands that in the 2026 landscape, the true winner isn't the one with the biggest power bill, but the one who can squeeze the most intelligence out of every single watt. We're witnessing the end of the brute force era and the beginning of a much colder, more physical reality.
That image is so perfect, isn't it? That immediate defensive crouch you saw, it really just captures the exact moment we're in right now in early 2026.
It's like a snapshot of an entire worldview getting challenged in real time.
It is, because we are standing at this massive fork in the road for how we as a civilization approach artificial intelligence. And that architect, deep down, he knows it, even if he can't say it out loud.
It feels like the entire narrative just shifted from under our feet. I mean, you think back just 2 years, maybe even 18 months ago, the only metric that anyone cared about was scale, parameter count, cluster size.
Right.
If you didn't have 100,000 GPUs on order, you weren't even considered a serious player. And now
it feels like the ground is moving.
And if you zoom out from that one conversation in Palo Alto and look at the macro picture, what you're seeing is a fundamental bifurcation of the entire global AI landscape. It's splitting into two completely distinct philosophies.
Okay, so let's break that down. What are the two camps? Well, on one side, you have exactly what your friend the architect represents. We can call it the brute force model. This is, overwhelmingly the Silicon Valley approach.
More is more.
More is more. It's defined by massive, almost unimaginable capital expenditure. It's about accumulating proprietary hardware, building these digital fortresses, and just accepting staggering energy consumption as the cost of doing business. It's the philosophy that says, if you throw enough money and enough electricity at a problem, you will win by default.
We build the whole bakery line. It's not just a boast, it's a strategy.
It's the entire strategy. But then you have this other side emerging, and it's emerging with incredible speed, mostly from the East and specifically from China.
And that's the efficiency civilization.
Exactly. And we have to be clear, this isn't just about being cheaper or, cutting corners, as your friend put it. It's a fundamentally different architectural philosophy. It's defined by things like algorithmic minimalism, by immense state capacity, and by a absolutely ruthless optimization of physical output per watt.
Output per watt, not just performance per chip.
That's the crucial distinction. And the stakes here, they're so much higher than people realize. This has stopped being a software race. We have to get out of the mindset of thinking of AI as just code or chatbots. This is now a contest of thermodynamics.
Thermodynamics. You're saying this is about physics now, not just computer science.
It's about physics and energy realism.
Yeah.
It's about the ability to deploy intelligence into the physical world, into our power grids, our shipping ports, our manufacturing plants, not just keeping it trapped inside a web browser.
And that very distinction, thermodynamics versus capital, is what we're going to dive into today. Because all the analysis we've been looking at points to this massive reality check hitting the tech world. and it's hitting hard. So let's start with the state of the West. There's this analysis describing the current situation as an inflection bubble.
It's a really fascinating and frankly pretty worrying analysis. When you look at the context of late 2025, bleeding into where we are now, the entire Western AI build-out looks like this inflection bubble.
Okay, let me stop you right there because bubble is a loaded word. When I hear bubble, my mind immediately goes to the dot-com crash. You know, pets.com, companies with zero revenue, a funny Super Bowl ad, and then poof. Sure. But the Magnificent Seven, Microsoft, Google, Meta, NVIDIA, these companies are absolute money-printing machines. They have billions, sometimes tens of billions in free cash flow every quarter. How can you possibly call this a bubble when the companies at the center of it are so profitable?
And that is a crucial distinction. It's why this is so dangerous. This isn't a valuation bubble based on hype like in 2000. It's an asset bubble, and it's based on the physics of depreciation. The analysis calls it the CapEx conundrum.
Break that down. CapEx, capital expenditure. It's just spending money on stuff, on gear. If I'm Ford and I build a new factory, that's an asset. If I'm Google and I build a new server farm, that's an asset. What's the difference? Why is one a conundrum?
Think about the useful life of that Ford factory, the building, the heavy machinery. It's going to be producing value for decades. If you built a railroad track in 1890, that steel was going to sit there and generate revenue for 50, 60 years. In corporate accounting, you depreciate that asset slowly because it retains its value.
Okay, that makes sense.
But AI hardware, it's not a railroad track, it's a banana.
A banana?
A very, very expensive silicone banana. It goes bad and it goes bad fast. Just look at the release cycles. NVIDIA's roadmap is public. They move from the Hopper architecture, the H100s, to Blackwell, to the next thing called Rubin. Each leap is happening in roughly 18 months to 2-year cycles, and the moment that new, more efficient chip drops, the economic utility of the previous generation, it just falls off a cliff.
So my friend in Palo Alto with his 50,000 H100s, the things he was showing me pictures of, like they were his kids.
He's the proud owner of 50,000 rapidly depreciating assets. Here's the core of the problem. Standard corporate accounting, the IRS schedule for computer equipment, allows them to write those servers off over 5 or 6 years. That's the rule.
But the reality?
The physical reality, the economic life, is that in 3 years, that H100 might be effectively useless for training a state-of-the-art model.
No.
Not because it's broken, but because the power-to-compute ratio will be so poor compared to the new stuff that it'll be financially ruinous to turn it on for a big training run.
So on the books, on their quarterly report to Wall Street, they're saying, this billion-dollar cluster is an asset that will last us 6 years. But in the real world, its competitive lifespan is half that.
And this creates what some analysts are calling phantom earnings. Their profits look artificially high because they aren't properly accounting for how fast their digital factory is becoming obsolete. If the revenue from all this AI investment doesn't skyrocket to a degree that covers that brutal 3-year depreciation curve instead of the gentle 6-year one, they're effectively just lighting cash on fire.
And the scale of that fire is what?
We're talking about projections of over $405 billion in aggregate AI capital expenditure for 2025 alone, just for the big players.
That is an astronomical number. It's like buying a whole fleet of Ferraris to deliver pizza, knowing that the Ferraris lose half their value every time you drive them off the lot.
And they're trapped in the cycle. They have to keep spending to stay on the cutting edge, but the very asset they're buying is rotting from the moment they plug it in. This is a fundamental tectonic shift in their business model.
From software to something else.
They are moving from being asset-light software platforms where you write the code once and can sell it 1 billion times with very low overhead to being asset-heavy industrial utilities. They're becoming more like power companies or railroad barons from the 19th century. But the crucial difference is their assets don't have the long-term stability of a power plant or a railroad track.
So there's the financial trap. But on top of the money, there's the physical wall they're hitting. The energy.
The energy ceiling. And this is the hard constraint. This is the part that no amount of creative accounting can hide from. Goldman Sachs put out a report estimating that AI will consume, get this, 19% of total data center power demand by 2028.
19%. That's a huge slice of a very big pie.
It's massive. And you're seeing the fallout already. There's this behind-the-meter scramble going on where tech giants are desperately trying to restart old nuclear reactors or making deals to monopolize entire renewable grids just to secure the power to keep these GPU clusters running.
I read about that. It feels almost dystopian. You know, these tech companies having to become their own private utility providers because the public grid simply can't handle their appetite.
But here is the fundamental bottleneck. The lead time to build new large-scale power generation, a new nuclear plant, a major hydroelectric dam, even a massive wind farm, is measured in years, sometimes a decade or more. The lead time to design and deploy a new cluster of tens of thousands of chips is measured in months. You cannot reconcile those two timelines. It's impossible. So what happens? The marginal cost of that next kilowatt of electricity goes up. It drives up the cost of compute, which compresses margins on all these AI products they're hoping to sell. The brute force model is running headfirst into the laws of physics.
Okay, so the West is hitting this ceiling, both financial and thermodynamic. At the same time, looking east, we just passed the one-year anniversary of what some people are calling the DeepSeek shockwave.
The DeepSeek revolution it's probably the most significant event in AI in the last 18 months, and it's still underrated in the West. It was a genuine shockwave. Because if you look back at the release of the DeepSeek R1 and V3 models, they fundamentally challenged the entire U.S. containment strategy.
The small yard, high fence strategy.
Exactly. The idea that by restricting China's access to the absolute top-tier chips, the H100s and now the Blackwells, the U.S. could effectively stifle their AI progress and maintain a lead.
It just didn't work.
It didn't work because the strategy was based on a flawed assumption. It assumed that hardware was the only variable that mattered. It assumed more transistors always equals more intelligence. DeepSeek proved that algorithmic innovation can be a powerful substitute for hardware superiority. They achieved performance that was comparable to the top-tier Western models, the GPT-4s, the Claudes of the world, using a tiny fraction of the compute and power.
What's the secret sauce? We hear these terms like MOE thrown around all the time, but what's actually happening under the hood that makes it so much more efficient?
It's not magic, it's just really, really clever engineering. The sources point to two main breakthroughs. The first is the mixture of experts, or MOE architecture.
Okay, mixture of experts. Unpack that for us.
Okay, so visualize a massive, dense, neural network like GPT-4 in its early days as a giant university faculty. Every single professor from every department. Now, every time you ask it a question, even a simple one like, what is 2 plus 2? You are forcing every single professor in that entire university to stop what they are doing, listen to the question, form an opinion, and then vote on the final answer.
That sounds exhausting. And incredibly expensive in terms of brain power.
It's incredibly energy intensive. That's a dense model. You activate all the parameters, all the neurons for every single token you generate. DeepSeek's MOE is completely different. It's like having a really smart receptionist at the front of the university. You ask your question, what is 2 plus 2? The receptionist sees it's a math problem and only wakes up the math department.
So the history department, the literature department, the philosophy department, they all stay asleep.
They stay asleep, they don't use any energy, you are only lighting up the small, specialized part of the brain that you actually need for that specific task.
So how big is the difference in practice?
It's massive. The DeepSeek V3 model has 671 billion parameters in total. Huge, bigger than most Western models. But for any given word it generates, it only activates about 37 billion of them.
So that's what, like 5 or 6% of the total brain is working at any one time?
Roughly, yes. And that means you need drastically less electricity to run the model for inference, for actually using it. This is how they completely bypass the chip restrictions. The US banned the H100s to stop China from having brute force power. DeepSeek proved you don't need brute force if you have elegance.
And there was a second innovation you mentioned.
Yes, something called multi-token prediction. Most models work sequentially. They predict the next word, and they take that word and predict the one after that, and so on, one by one. DeepSeek's architecture allows it to predict several future words all at once. It's kind of like a chess grandmaster who sees 3 or 4 moves ahead instead of just the very next move. This dramatically speeds up the inference process and reduces the overall cost per token generated.
The significance of this really can't be overstated, can it? It basically proved that the scaling laws, the simple idea that you just keep adding more chips and more data to get smarter models, aren't the only path forward. Algorithmic minimalism can let you do more with less. And this brings us to the real-world application of this whole philosophy.
Yes, where the rubber meets the road.
This is where it gets really compelling for me. I've been spending a lot of time lately tracking these tectonic shifts. And if you follow my work, you know I'm obsessed with this intersection of the physical and the digital. We talk about AI as this ethereal thing in the cloud, but it's really made of copper, silicon, and just immense amounts of electricity. Looking at the data coming out of the East, it's clear we aren't just watching a software update, we're watching a civilizational pivot toward what I call energy realism.
Energy realism, it's a very precise term for what's happening.
To make this real for people, I've kind of gathered 3 perspectives that put a human face on this cold logic of algorithmic efficiency. The first one comes from the Ningxia Desert in western China. I was reading a dispatch about a grid engineer there, a guy named Qwen. He works at one of these absolutely massive ultra-high voltage UHV power hubs.
Right. The UHV grid is really the backbone of China's entire energy strategy. It's a colossal piece of engineering.
It's incredible. And you have to try to imagine Qwen's environment. It's this vast, dusty landscape, and it's just covered in square miles of solar panels and wind turbines. For years, his job was an absolute nightmare.
Why is that?
Because managing the surge of all that intermittent renewable power into the national grid was this frantic manual balancing act. A cloud passes over the solar farm and gigawatts of power just vanish. A huge gust of wind hits the turbines and you get a massive power spike. He was constantly on the edge, trying to prevent flicker and instability while pushing thousands of megawatts of power toward the industrial coast, thousands of kilometers away.
And flicker or instability on a grid of that size isn't just an inconvenience. It can cause blackouts, damage, incredibly expensive infrastructure.
But recently, they integrated a lightweight, high-efficiency AI model directly into the dispatch system. And this is the key point. This wasn't some bloated general-purpose Western LLM trying to chat with him about the weather. This was a lean, minimalist algorithm designed for one purpose and one purpose only: real-time precision optimization. Qwen describes watching the monitors now as this AI micro-adjusts the flow of 1 billion volts in real time, predicting lulls and surges seconds before they happen.
It's like algorithmic alchemy.
That's the perfect phrase for it. By shaving off milliseconds of latency and optimizing every single electron, the system does more with less. And for Qwen, the AI isn't some god in a box. It isn't a chatbot. It's a digital artisan's tool. It's the difference between using a sledgehammer and a surgeon's scalpel. When I read that, it hit me. This isn't just about code anymore. It's about a culture that treats 1 kilowatt-hour of energy as a sacred resource to be squeezed for every last drop of intelligence. It's engineering minimalism as a survival instinct.
That story about Qwen, it's a perfect microcosm of the broader national strategy that we see laid out in the analysis. It connects directly to this massive infrastructure project called Eastern Data, Western Computing.
Eastern Data, Western Computing. That sounds like one of those big state slogans.
It is, but it's also a direct solution to the physics problem we talked about earlier, the energy problem. Instead of trying to pipe all that electricity from the sunny, windy west to the data centers in the crowded coastal cities in the east, which is lossy and inefficient,
you move the data centers to the power source.
Exactly. It's a top-down strategy to build a national computing grid that functions just like the power grid. You move the compute to where the energy is abundant in cheap places like Ningxia. You're moving the mountain to Muhammad, or in this case, the data center to the sunlight.
And this is all centrally planned.
Centrally planned and with incredibly strict standards, the government is mandating power usage effectiveness, or PUE, for these national data hubs. They're required to hit a PUE of 1.25 or lower.
Okay, a PUE of 1.25. For listeners who don't run server farms, put that in context. Is that good?
It's incredibly efficient. A PUE of 1.0 would be perfect, meaning 100% of the power goes directly to computing with zero waste. A PUE of 1.25 means that for every watt used for computing, only 1/4 of a watt is wasted on things like cooling and overhead. Many older Western data centers can operate at 1.5, 1.6, or even higher. This isn't just market forces at work. This is a state mandate. They are treating compute as a national utility that must be optimized, not as a luxury product for a private company.
It really does seem like the West is playing a game of who can raise the most money to buy the most GPUs, while the East is playing a completely different game of who can waste the least amount of energy.
That's a very sharp way of putting it. And this efficiency-first mindset is now rippling out way beyond China's borders, and it's creating a whole new geopolitical dynamic. This brings us to the concept of sovereign AI.
Right, I was looking at that Tony Blair Institute report you mentioned. It talks about this global struggle for nations to maintain agency.
Agency is the key word there. They break it down into 3 parts: control, steer, and depend. The report argues that in the 21st century, no country can be fully self-sufficient in tech, but they have to avoid becoming helplessly dependent. And we're seeing a clear divide emerge between taker dependence and maker dependence.
Taker dependence sounds pretty self-explanatory. Just take what you're given.
That's exactly it. It's the trap of relying on closed, proprietary Western black boxes. If you're a developing nation in, say, Africa or Southeast Asia, and you build your entire digital infrastructure on a proprietary model from a U.S. tech giant, you are completely subject to their rules, their pricing, their content filters, their data privacy policies, and crucially, you're subject to the whims of their government's export controls. You are a tenant living in their digital house.
And the rent is always going up.
The rent is definitely going up, and you have no idea what's happening inside the walls of the house. You just have to trust the landlord.
This connects perfectly to the second perspective I found. I was following this fascinating thread online from a tech lead in Jakarta. He's part of a local computing power sovereignty initiative in Indonesia. For years, his firm was stuck in that exact Western stack trap you just described.
And what specific problems were they running into?
It was a nightmare of cost and latency. They were trying to build a system to manage logistics for shipping across the Indonesian archipelago. I mean, you're talking about thousands of islands. It's a logistical nightmare. They were paying these massive subscription fees for proprietary US AI models to try and optimize routes. But even worse than the cost was the latency.
The speed of light is a hard limit.
Sending data from a ship in the Java Sea to a server in Oregon and then getting a response back was just too slow for real-time tracking and rerouting.
Yeah.
And they simply couldn't afford the specialized hardware required to run those big Western models locally.
So they were completely priced out of the brute force model.
Totally. Then, as he describes it, the algorithm Silk Road opened up. They started experimenting with and then deploying these open source, low latency models being developed in China, things like Alibaba's Qwen and DeepSeek. These models are specifically designed to be efficient, to run on modest, even consumer-grade hardware, not just supercomputers. And the change was incredible. He wrote that for the first time, his team felt like they weren't just digital tenants renting technology from Silicon Valley. They were actually building their own local logistics AI for their own specific problems. He described it as finding water in a drought. For them, this isn't about geopolitics, it's about the dignity of tech autonomy. By bypassing the high-entropy, high-cost models of the West, they're helping build a new Eurasian tech standard that actually fits the physical and financial reality of the global South. It made me realize that sovereignty isn't just some abstract political concept. It's the ability to run your own civilization on an algorithm you can actually afford to power.
That phrase, finding water in a drought, that's incredibly telling. This is precisely what the sources are referring to as the pluralization of AI. The de facto monopoly held by a few Western tech giants is being fractured by the proliferation of these high-performance open-weight models.
It's interesting you mentioned Qwen as well, not just DeepSeek.
Yes, Alibaba's decision to open source over 100 of their models was a huge strategic move. What's happening here is a different kind of export strategy. China isn't just selling a finished product like a subscription to ChatGPT where you just pay a monthly fee. They are exporting development toolkits.
A toolkit, not a service.
Right. They're giving these countries the model weights, the deployment schemes, the architectural blueprints. They're essentially saying, here's the engine and here are the plans. You go build the car that's right for your country.
And for the global South, for nations in Africa, Southeast Asia, Latin America, that has to be an infinitely more appealing proposition than getting a high-cost service packaged with a lecture on AI ethics from a company in California.
It appeals to pure pragmatism. It's a pragmatic alliance. And it also helps solve another huge problem, the data scarcity issue. The sources mention that Common Crawl, the massive data set most big Western AIs are trained on, is overwhelmingly English. Languages like Arabic, Chinese, Indonesian, Swahili, they're massively underrepresented.
So the models are culturally and linguistically biased from the start.
Deeply. These sovereign AI initiatives allow these nations to take a highly efficient base model, like DeepSeek, and then fine-tune it locally on their own data, in their own language, reflecting their own culture, without having to send all that sensitive national data back to a server in the US.
It's a genuine democratization of the technology, but it's based on lowering the physical barrier to entry. If you don't need a nuclear power plant to run your model, then suddenly you can have a thriving AI ecosystem in Jakarta, or in Nairobi, or in Bogota.
Exactly. It's fundamentally shifting the global power dynamic from who owns the intellectual property to who can actually deploy the utility.
But let's look at the flip side of this. We've talked about the efficiency emerging from the East and the hunger for autonomy in the global South. What is actually happening inside the machine in the West? We touched on the financial bubble, but what about the culture? The third story I found really highlights the deep frustration there. There's this narrative circulating among disillusioned developers in Palo Alto that paints a picture of what I can only call financialization entropy.
Financialization entropy. That sounds ominous.
It's brutal. I was reading an account from a senior engineer, a brilliant guy, top of his field, who spent 18 months at one of the top-tier AI labs. He told a friend that in that entire year and a half, he spent almost no time actually coding or doing research. He spent his time in lawfare meetings.
Lawfare. What does that even mean in this context?
It means he was constantly in meetings with lawyers, navigating ESG compliance reports, arguing with local city councils about power and water permits that were stuck in 5-year bureaucratic backlogs, and generating endless presentations for investors to justify the company's massive burn rate. He described the whole atmosphere as shoveling gold into a furnace just to keep the lights on and the lawyers paid.
That is the very definition of entropy. It's energy that is lost to heat, or in this case to bureaucracy and legal friction, rather than being used to do useful work.
And you contrast that with the stories of state capacity we see emerging from the East, where the distance between a research breakthrough in algorithmic compression and its physical deployment in a smart port is shortened by a national mandate. While that Silicon Valley engineer is trapped in this web of regulatory complexity and capital bloat, where pouring more money into the system somehow results in slower physical progress, his counterparts in the East are operating with this lean, almost militant focus on physical output hegemony. It's a really sobering contrast. I look at these two worlds and I see this bizarre inversion of the old script. The West has all the capital, but it feels like the East has all the velocity.
That term you use, financialization entropy, it comes directly from the analysis on the economic geography of AI. It discusses this concept of rentiership.
Rentiership, as in collecting rent.
It's what happens when an economy shifts its focus from producing new, tangible goods and services to simply extracting rent from assets it already controls. Things like intellectual property, access to a platform, or complex financial instruments. The engineer in your story is trapped in a system that is now optimizing for stock price, for building moats to keep competitors out, and for regulatory capture to protect its position.
So the primary goal shifts. It's no longer, let's build the best, most efficient AI. It's, let's protect the valuation of our company at all costs.
To a significant degree, yes. When innovation is driven primarily by the need to justify that massive CapEx to shareholders and keep the stock price climbing, you get the risk of this inflection bubble. You get entropy. Energy is just wasted on friction, legal friction, bureaucratic friction, financial friction.
And how is the East avoiding that trap?
The Synalytics report describes the state capacity model with this phrase, grasping with both hands.
That sounds like a kung fu move.
It's a policy directive. With one hand, you have strict security and ideological control, content moderation, enforcing socialist core values. We can't ignore that part. It is a highly constrained system in terms of speech and information. But with the other hand, there is massive coordinated state support for innovation. Direct subsidies, government-run data exchanges, fast-tracked infrastructure build-outs.
It's like building a frictionless tube for engineering to happen inside of.
It's vertical integration on a national scale. The report notes that a staggering 61% of all large model procurement in China comes from state-owned enterprises. The state grid, the big oil companies like CNPC, the shipping conglomerates, the government itself is the biggest customer. And they are not buying AI to write better marketing copy or generate poems. They are buying AI to optimize the power grid, to find new oil deposits, to manage port logistics, to run the entire industrial base of the country more efficiently.
This connects directly back to what we said at the very beginning. The West is building ever more sophisticated chatbots. The East is building a digital nervous system for its physical industry.
And this leads us directly to what has to be the physical endgame for all of this. Because eventually, intelligence has to leave the server and enter the real world. We are rapidly transitioning to the era of embodied intelligence.
Robots.
The consensus is growing, almost universally, that true artificial general intelligence, real AGI, will require a physical body. It needs to be able to interact with the world, to learn from cause and effect in 3 dimensions, to truly understand concepts like physics and space. And this is where China's existing advantage in the application layer becomes, frankly, a terrifyingly real competitive advantage.
Because they make everything.
They make everything. They have the entire manufacturing supply chain. If you want to build 1 million humanoid robots, you need 1 million high-torque servos, 1 million high-density battery packs, tons of rare earth magnets for the electric motors. Where do you get that stuff? At scale, quickly, and affordably. You get it from the Chinese supply chain. The analysis highlights examples that are already being deployed, like Xpeng's Iron Robot, a humanoid designed specifically for manufacturing tasks, and Hare's Quavo robot, which is being developed for domestic home scenarios.
I saw a video of that Xpeng robot, and what struck me was that it wasn't dancing or doing backflips like some of the Boston Dynamics demos we see. He was just standing on an assembly line, methodically putting parts into a car. It was working. It was boring, and that's what made it so powerful.
That is the exact difference. They are focused on the transition from digital AI agents that live on a screen to embodied intelligence that works on the factory floor.
So if you combine the hyper-efficient algorithms, the DeepSeek-style minimalist code,
Right,
and you put that software brain inside a robot body that you can manufacture at an unprecedented scale because you own the entire supply chain.
then you have a truly formidable, perhaps insurmountable advantage. And it all comes back to energy realism. The 21st century hegemon will be the civilization that can most efficiently convert 1 degree of electricity into the most intelligence and then most effectively apply that intelligence to generating physical output.
The math of the kilowatt becomes the math of power.
The Eastern strategy, as outlined in the sources, is a multi-pronged approach to this. They're investing heavily in next-generation energy like nuclear fusion research. They've built out the UHV grids to move power efficiently, and they have a specific national energy AI integration plan with concrete 2027 targets. They are integrating the AI directly into the energy production and distribution cycle itself.
Meanwhile, the Western strategy seems to be like tech companies buying up old nuclear plants for their own private data centers.
It's financializing the energy supply, buying the asset to secure the moat for your own company. It's fundamentally a defensive move designed to protect a private interest, whereas grid-level optimization is an offensive move designed to advance a national one.
It honestly feels like we are watching two different species of evolution playing out in real time. One is becoming this giant, hungry, magnificent dinosaur that needs an entire forest's worth of energy just to survive. And the other is evolving into something leaner, smaller, faster. A mammal that can survive on scraps and outmaneuver the giant.
And in a resource-constrained world, which is the world we actually live in, efficiency almost always wins out over brute force in the long run.
So let's try to bring this all home. We've really met three characters in this deep dive today. We have Lao Shen, the grid engineer out in the desert, using a minimalist AI to balance 1 billion volts of green energy. We have the developer in Jakarta finding a new kind of sovereignty and open source code that lets him run his country's logistics without paying rent to Silicon Valley. And then we have the brilliant architect in Palo Alto, trapped in a system that has him shoveling gold into the furnace of a massive, rapidly depreciating cluster, drowning in financial entropy.
These aren't just anecdotes, they are signal flares. They are telling us that the era of brute force, the Gilded Age of just throwing money and watts at the problem and assuming you'll win, is coming to an end. We are entering the era of the efficiency civilization.
When you look at these three snapshots, it's very easy to get swept up in a simple us versus them narrative. But as someone who analyzes these trends, I have to step back. While that state capacity model offers this terrifyingly efficient speed and solves the energy intelligence equation in a beautiful way, we also have to recognize the human cost of that kind of singular focus. There's a real tension between the minimalist engineering that drives the Eastern efficiency and the messy regulatory democratic debates of the West. That entropy we talked about is in some ways the price of a loud, litigious, but ultimately more open society. However, we cannot ignore the math. If one civilization can consistently convert 1 degree of electricity into 10 units of applied intelligence, while the other only gets 2, the winner of the 21st century might already be decided by the cold, hard laws of thermodynamics. We are moving away from the era of brute force and into the era of efficiency civilization. It's not just a tech shift, it's a reality check for the entire planet.
It truly is, and I think that reality check is going to redefine not just the tech industry, but the entire geopolitical map of the next decade and beyond.
You know, we always assume that the smartest AI will be the one that knows the most facts or can write the most beautiful poetry. But what if the smartest AI is simply the one that can keep thinking when the power gets scarce? What if survival of the fittest applies to our algorithms just as much as it applies to us?
That is the ultimate question, isn't it?
We'll have to wait and see who survives the coming winter. Thanks for diving deep with us.